Today we are going to be talking about operational amplifiers. Operational amplifiers, or op-amps for short, are relatively ideal amplifiers which provide large voltage and current gain, large input impedance, and small output impedance. Op-amps were originally designed in the 1940s to perform mathematical calculations for analog computers. These original versions used vacuum tubes. Today's models, however, use transistors. This allows them to be both small and inexpensive. The standard symbol for an op-amp is shown on the bottom left here. A basic op-amp has 2 input ports and 1 output. Note that while the figure shows in plus and in minus, this does not mean that the input values must be greater or less than 0 respectively. It simply indicates which is taken as the higher and lower potential when amplifying the voltage difference between the 2 terminals. The symbol can also include terminals for the bounding supply voltages plus VCC and minus VCC as shown. These voltages limit the output of the op-amp to no higher than plus VCC and no lower than minus VCC. We could redraw these connections for the controlling voltages as shown on the right. An op-amp is composed of tens of transistors. The figure here shows the internal makeup of the very common LM741 op-amp. The different transistors form different types of amplifiers and other elements that work together to provide the high gain, high input impedance, and low output impedance that characterize standard op-amps. Analysis of this full circuit, however, is beyond the scope of this introduction and is not necessary, as good analysis and design of op-amp circuits can be achieved with a much simpler model of an op-amp. Op-amps operate in one of 2 major modes. During normal operation, i.e. when the output is not bounded by the supply voltages, the output significantly amplifies the voltage difference between the 2 input terminals. If the output is bounded by either the low or high supply voltages, then the op-amp is said to be operating in saturation. Our main focus will be on analyzing circuits assumed to be in the normal operation mode. A model for an op-amp in normal operation is shown on the bottom left. A dependent voltage source amplifies the voltage difference between the 2 input terminals. As already mentioned, the input resistance Ri is typically quite large, the output resistance Ro is small, and the gain A is very large. Typical values for these parameters are shown on the right. We are now going to look at a common op-amp configuration shown on the left. In this configuration, 2 resistors have been connected to the negative input terminal of the op-amp. An input voltage V1 is applied to the positive input terminal, and the output V2 is read at the output of the op-amp. If we replace the op-amp with the model circuit just shown, we get the diagram on the right. While we could analyze this circuit and find a relationship between V2 and V1, the analysis is non-trivial. Instead, we will take advantage of the typical characteristics of some of the key parameters of an op-amp. We can notably simplify the analysis and arrive at the same result. We have already mentioned that the input resistance of typical op-amps is very large and the output resistance is very small. Large resistance values, especially those in the mega, giga, or even larger ohm range, can generally be modeled as an open circuit. Similarly, very small resistance values can be modeled as short circuits without significantly impacting the analysis. If we apply both of these simplifications, we get an equivalent circuit that looks like that shown on the right. Using this new model, we can relatively easily come up with a relationship between V2 and V1. We can first recognize that the voltage at V2 is equal to the voltage of the dependent voltage source AVN. We know that Vn is equal to Vn plus minus Vn minus, giving V2 equals A times the Vn plus minus Vn minus. We now want to find relationships for Vn plus and Vn minus. Since Vn plus is only connected to V1 and is an open circuit, Vn plus simply equals V1. The voltage at Vn can be found by applying a voltage divider between R1 and R2, leading to Vn minus equals R1 over R1 plus R2 times V2. If we substitute the equations for Vn plus and Vn minus into the first equation, we get V2 equals A times V1 minus V2 R1 over R1 plus R2. If we rearrange, we get V2 times 1 plus A times R1 over R1 plus R2 equals A times V1. Rearranging further, we can get that V2 over V1 equals A over 1 plus AR1 over R1 plus R2. Since A is very large, the term AR1 over R1 plus R2 in the denominator should be significantly larger than 1, and so we can ignore the 1. This results in a further simplification of V2 over V1 equal to A over A times R1 over R1 plus R2, which can be further simplified into R1 plus R2 over R1 and further to 1 plus R2 over R1. This circuit is known as a non-inverting amplifier. Its output voltage V2 is 1 plus R2 over R1 times larger than the input V1. The non-inverting in the name implies that the output has the same sign as the input. While this model made analysis fairly straightforward, there is another simplification that can often be made that makes analysis even simpler. We already mentioned that the voltage gain A of an op-amp is very large, typically greater than 100,000. Due to this large gain, if the op-amp is to stay within the normal operating region, Vin, the potential difference between the two input ports, must be very small. As an example, for an op-amp with a gain of 100,000 and a max output of plus minus 10 volts, the input difference at the input can be no more than 0.1 millivolts. This is rather small. If the op-amp gain is even larger, the allowable difference is even smaller. This leads to the model simplification that the difference in voltage between Vin positive and Vin minus must be essentially zero. Looked at another way, the voltage at in plus and in minus must effectively be the same. As a note about this assumption, it applies only when feedback from the output is applied to the negative input in minus. This is known as negative feedback and applies to our example as the output fed back into the input in minus through the resistor R2.
Negative feedback prevents the voltage difference between in plus and in minus from running away. As the voltage at Vin plus increases, the output voltage increases. Since the voltage Vin minus is tied indirectly to the voltage Vout, Vin increases when Vout increases. Since Vin increases, the difference between Vin plus and Vin minus decreases, and so the output voltage stabilizes. We are now going to reanalyze our example circuit employing our new op-amp assumption. We know that the voltage at in plus equals V1.
Since we now assume that Vn plus equals Vn minus, this means that the voltage at in minus is also essentially 1. Since our first assumption said that no current flows into the input of an op-amp, this means that resistors R1 and R2 form a voltage divider with V2. The voltage divider would lead to a relationship Vn minus equals R1 over R1 plus R2 times V2. We already said that Vn minus also equals V1, which leads to V1 equals R1 over R1 plus R2 times V2.
This can be simplified to V2 over V1 equals the quantity R1 plus R2 over R1, which further equals 1 plus R2 over R1, the same result we got with our previous analysis. Arguably, this analysis was even simpler than the first and removed the need to make any statements about how a relationship simplifies as the gain gets very large.
As a summary of our introduction to operational amplifiers, we generally make two assumptions about op-amp behavior. The first is that no current enters either of the op-amp input ports, in plus or in minus. The second, which applies for cases with negative feedback, is that the voltage at both input terminals is the same. These two assumptions combined allows the analysis of op-amp circuits without requiring significant amounts of mathematical manipulation.